This is PreCalculus Unit 7.5 Math Analysis, which is going to be linear programming. We've talked about matrices, and now we're going to talk about linear programming in order to maximize solutions in a feasible area. First, a definition. The process of finding the best possible solution is called optimization. Think about finding a maximum or minimum of a parabola, something that we've all done in the past. But when the constraints, and in our case, these constraints are going to be equations or inequalities, are strictly linear, we will call the process linear programming. Very different from computer science programming. Okay? Strictly graphical, straight lines, inequalities. We will usually start with an objective function. And that is going to be of the form f of x comma y. So this is going to be a function in two variables equals ax plus by plus c. There's a couple things we want to note here. First of all, it does not have to be strictly in two variables. You could have a function in 3 or 4 variables. And you could also have a system of equations along with those variables that creates a 4x4 matrix of equations. So the problems can get pretty difficult, but there are a lot of good applications. So we also want to say here, the constraints are going to be inequalities. That is quite a lot of definition there, so why don't we take a look at an example and it will make more sense. Graph each inequality and graph the solution set. The first one is y is less than 2x, less than or equal to 2x. So I'm going to graph y equals 2x. And then I'm going to graph x is greater than or equal to 0. So x equals 0, remember x equals 0 is going to be a vertical line. And then y is less than or equal to negative x plus 6. So now I'm going to graph y equals negative x plus 6. So let's start at 6 and go down. Graph the solution set. Okay, so the first one is less than 2x, which means we're going to be below the blue line. And then the next one, x is greater than or equal to 0, so we have to be to the right of the green line. And then y is less than or equal to negative x plus 6, so we have to be below the light blue line. There's a lot of shading going on there, but where do all three solutions intersect, that's going to be this area right here. It's a little bit of review for you. Hopefully you've seen that before. Now, suppose that you wanted to maximize some random expression, 3x minus y. Where would the maximum value occur such that it is in this region? Well, I might take a look at, say, the highest point here. This point is going to be 2, 4. And then there's another point I could consider, 0, 0. See how that's a vertex? So now, if I take 2, 4, and I plug that into the expression 3x minus y, I would get a value of 3 times 2 minus 4, and that's going to be 6 minus 4, which is 2. If I tried the other one, 0, 0, I would get an answer of 3 times 0 minus 0, which is 0. So if I take a look at these two things, what's the maximum value? The maximum would be 2. It's a single number. So that is my max. It seems intuitive at the moment because it's the highest point. Okay, so what we have done is a little bit of linear programming to find the best solution. Now, note that if we want to find an optimum value for the previous example, we need to plug in values. Specifically, plug in the vertex or vertices. For our purposes, an optimal solution will only occur at a vertex of the feasible region. There's a few things going on here. First, for now, understand that we just have to look at the vertex of the shape that we make. This one's kind of like a house, and it goes on forever that way. The second thing is, what is feasible region? The feasible region is the same thing as the solution set. So here's a process for finding the optimal solution using linear programming. First, graph the region. Remember, these are all going to be linear functions, so they should all be straight lines. Find the coordinates of each vertex. Plug in the vertices to maximize or minimize. We can do both. The objective function f. Usually some function of two different variables. Okay? We're used to thinking of things three-dimensionally now. So if you have a function f in x and y are two variables, and you can get that third dimension by getting whatever f is. In this case, f was 2. Let's try another one. Different kind of wording, okay? but let's maximize the function f of x comma y equals x plus 2y, subject to certain constraints that x plus y is less than or equal to 6, x is greater than or equal to 0, and y is greater than or equal to x. So step number 1, graph each inequality. That's going to be x plus y equals 6. And also notice that these lines are going to be solid lines because these are all greater than or equal to or less than or equal to. So check. X is greater than 0. Y is greater than or equal to x. Check. All right, next step. Let's graph the solution. The solution area should be x plus y is less than or equal to 6. So it's going to be below the blue line, to the right of the purple line, and above the green line. So it's going to make this triangle right here. Okay, next. Find some vertex that maximizes x plus 2y. So the coordinates of each vertex, let's call them A, B, and C. So vertex f of x comma y, we're going to make a little table. A is going to be 0, 6. B is the point 3, 3. C is the point 0, 0. And when I plug each of those coordinates in for x and y, x plus 2y for coordinate A would give me 0 plus 2 times 6, which is 12. The next one would be 3 plus 2 times 3, which is going to be 9. And then 0. So which vertex gives us the maximum of the function? It would be point A. All right, that is all for today. Please comment on this video in order to receive credit, and then have a nice day.